Yeah. Please go ahead, Shamil.
Right, just a minute, sir. Yeah. Hello everyone. Today we have with us Professor J.V. Gemert. J.V. Gemert received his PhD degree from the University of Amsterdam in 2010. There he was a postdoctoral fellow as well as he was the postdoctoral fellow at École in Paris. Currently he leads the Computer Vision Lab at Delft University of Technology, where he teaches deep learning and Computer Vision MSc courses. His research now focuses on visual inductive priors for deep learning for automatic image and video understanding. He has published over 75 peer-reviewed papers with more than 5,000 citations. We are elated to host you, sir, and I'm also going to share the link, the very useful link of your page where you've suggested the research guidelines. Please proceed,
Yeah.
sir.
Please go ahead, Dr. Yan. Please go ahead. Dr. Yan, you're on mute. Oh, sorry. Yeah. Can you unmute now? Yeah.
Yes, sorry,
Sorry.
I muted myself, but then I was no longer allowed to unmute. So thank you very much for the invitation. Yeah, so this paper was presented at the BMBC this year. And well, it's about black magic. And it's about black magic in deep learning. And what we call black magic is, well, the human skill. So there is a human involved in training all these deep networks, and the quality, so the how good your human is affects the results of training your deep network. And that's what this paper is about. And it's interesting because I pitched this idea to do such a paper. I pitched it to several students. Yeah, but none of my students found it interesting until Kanav came. And so he's a master student, and he did this for his master thesis. Yeah, but I think many students now, they're more interested in, well, developing new architectures.
Yeah.
This paper is a bit different, so it's about, well, really understanding something about how much skill, is there a correlation between skill and accuracy? And in a way, I like these kind of questions because it doesn't really matter what comes out.
Yes.
So if you do a new architecture, and if you have and you want to always improve accuracy, yeah, there may be a risk that you don't improve accuracy, and then you have a problem.
Yes.
And of course, the goal of science is to understand things. Yeah, not necessarily improve, but okay, it would be nice if it improves. And of course, understanding really helps to improve stuff. But okay, let me start with this presentation. So, well, if you listen to the deep learning, well, fathers, so Jan de Koen, for example, he so in the deep learning paper that I have in Nature, they say, well, deep learning, the nice thing about this is that we don't have to do this handcrafting of features anymore. So back in the day when I did my PhD, there were SIFT descriptors which were handcrafted. It was a very good descriptor. It still is for image matching. It still does well. And then we extracted features first, and then we fed these features to a classifier. A classifier could be a deep network, but typically we didn't use neural networks back in those days because neural networks are quite, well, they're a bit annoying because you need to set many hyperparameters. If you do a support vector machine, you typically have the C parameter, and back in the day, well, we just set it to 1, and then you typically got good results. But now you have to set the number of layers, you have to set the number of neurons, you have to choose your optimizer, choose your learning rate, choose your learning rate decay. There's all kinds of things that you have to set. So that was why in the past we didn't use neural networks as much, because we used handcrafted features. But deep learning says, okay, no more handcrafting features. We're going to learn the features for you. Okay, very good. What's happening now then is that people are now handcrafting their architectures. So they're now designing the architectures. Do you have batch norm? Do you not have batch norm? Do you use this layer, more layers, less layers? So they're handcrafting the architectures, but also they're handcrafting the optimization of them. So when to change your learning rate? What is your learning rate? Do you use momentum? So these hyperparameters, this optimization of your network architecture, that's now where the handcrafting has gone to. And this is indeed also what we call black magic. And there is a huge number of these things. So there's learning rate, batch size, momentum, number of epochs, learning rate, 2 times even learning rate. That's how important it is. Oh no, learning rate decay. I should finish my sentence. Number of layers, number of neurons, all these kind of hyperparameters are all things you have to set. Typically, they are set beforehand. And well, we found that setting these hyperparameters, they're quite essential. They're essential for making good comparisons, and they're essential for guaranteeing that work can be reproduced. So doing a reproduction is, of course, a very good scientific practice. So there are these papers by Google on, for example, where they have huge amounts of resources. And one example is that they evaluate some guns. So you have the generative adversarial networks. They take some papers, they compare these papers against each other, where they actually do a very good, thorough sweep of hyperparameters. And then they actually found out that, well, these improvements that all these papers claim, yeah, these all kind of disappear if you set the hyperparameters, the baseline, quite well. So the same has recently been shown for metric learning. So if you do the vanilla metric learning, the contrastive loss, it performs quite well. And the same has been shown in natural language processing. So if you set these hyperparameters, that can actually give you state-of-the-art results. It can have a similar effect as a whole new architecture, a whole new algorithm. So they're quite important. Now, there is work that tries to automate this, and I think that's good. So you should automate setting these hyperparameters. So you want to do machine learning, so you want the machine to do the work. But in practice, yeah, there is a grad student or a data scientist somewhere involved that does the tuning. There is a human typically involved in every training of every deep net. That human then sets the parameters, optimizes them, becomes really the expert on the problem, and that human is in practice doing the tuning. So there's much hidden knowledge in your human that comes with your network. In this paper, we try to investigate, well, how large is this role now of this human expert? So if you have any questions, feel free to ask. I don't know if there is a chat.
Yeah. We'll interrupt you, Jan. We are
Okay,
monitoring the chat box. We'll definitely interrupt you.
Great. Good. Now, what we did, we okay. So now, okay. Yes, please post questions if you have them. So what we did in this paper, so we did a user study. So we did a user study where the hyperparameter tuning was fully controlled. So that means that every participant gets to tune the same hyperparameters with exactly the same random seed for initialization, also with the very same batch samples. Everything is exactly the same for every user. And this is exactly what we want to test. So the environment is completely controlled. And then we want to find correlations of experience, how experienced a user is in deep learning, with accuracy and speed of optimization. And we investigate a bit on what kind of search strategies people use, and we make some recommendations for reproducibility and comparisons, making comparisons between models. Now, what we did, so we took a kind of a standard deep learning setup, and we took this ImageNet data set. So you have to pronounce it a bit with a French accent. 10 classes from ImageNet. It has 13K training samples, 500 validation, and 500 tests. We didn't tell our participants. So we just told them it's a 10-class image classification problem. And that's the only thing we told them. We didn't tell them it was this data set, because otherwise some hidden knowledge may sneak in. And then, okay, if you're tuning hyperparameters and if you're training deep networks, well, you don't want to wait for 2 weeks before you have some results. So indeed, the task has to be a bit smallish, so 13,000 training samples. And also the models should be somewhat, not too large, because you want to get some results quickly. So we took SqueezeNet. That still gives relatively good accuracy, but is not too long to train. And then we gave a list of hyperparameters. 4 of them were mandatory and 11 were optional. Now, what we then did is, for the participants, well, we have to give them some sort of user interface. So we try to mimic the natural environment where your data scientist, where your human expert, where that human expert lives. So he lives using, I don't know, TensorBoard or something where he's training the network. So we try to get a good web interface where you can see the loss during training and give some options for early stopping. And the task then that we asked them to do, okay, you get 2 hours maximum, and after 2 hours maximum, you have to submit your final recommendation for the parameters. And then we took those parameters. So after we done all the experiments, for every participant, we took the best parameters and we trained on the train and the validation set, and then we evaluate this on the test set. And we did this then 10 times for 10 different random initializations. So there the seed is 10 times changed. So that means that the initialization of the network is different, but also the samples that are chosen in your batch are also different. And then we did this 10 times to make sure that you get some mean and some standard deviation, so that you can actually compare some things. And then here, what you see on the left, here are the hyperparameters. So the 4 mandatory ones is, okay, how many epochs do you want to do? What's your batch size? What is your loss function? So you can of course choose softmax, but you don't have to. What optimizer do you use? And then below there are some optional ones. So learning rate, weight decay, momentum, different. If you choose Atom, for example, you get some other hyperparameters than if you choose SGD. So these parameters, we also gave them as optional, but we set them to a default value. And on the right, what you see is a histogram of the accuracy. Here we just ran our, we just took random hyperparameters and we just did some runs to see is there actually some variance here. So we did 320 random hyperparameters. We just drew 320 different numbers here, and then we looked at the validation accuracy. And then what you see in this histogram, well, there's quite some between 10 and 20. There's even 100 runs there. So random. So if you set them wrong, you get everything is assigned to one class, so you get nothing. And well, between 70 and 80, they're still around a bit more than around 70. So there are good values there, but there's also quite some spread in the middle. So of course, it would be bad if we chose a model that always does well or always does bad. So there has to be some variance, and that seems to be the case. So these hyperparameters, they do allow for some variance. So there can be variation in this. Oh, and now here are some of the results. So in total, we had 463 combinations of hyperparameters from 31 participants in our study. And in the graph, what you see here, I'm not sure if you can see my mouse, but here on the left, the graph, this is a histogram with the number of participants here on the y-axis, and the experience in deep learning in months on the y-axis. And so you can see there's quite some who actually didn't have any experience at all. And there's a few that had more experts, and there's some in the middle. So we grouped them into 3 of these groups. So novice would have 0. So these are just people who kind of managed to convince to participate in the experiment, but they didn't know anything about deep learning. Some people with medium and some experts. And then what you see then here in the middle plot is it's a box plot. So the mean is here given by the triangle, and you see, I think the strip, the vertical line is the median, and here is the standard deviation, and the size of the box tells you the spread. So you see that novices, there's quite a huge spread here, and the mean, well, it's around 40% on average. If you have medium experience, the spread becomes less. Also, the mean all of a sudden is around 65. And the experts, well, they have around 5% differences, but the mean is already around 75%. So there's a huge difference between these 3 groups. And we did our statistical tests on this, and we can show that there is actually statistical significant difference between these groups. And one thing that's interesting is that, so even among experts, there is this 5% difference. So if you are an expert and we're both experts, we both know what we're doing, yeah, there may be even a 5% or maybe 3% difference between the hyperparameters that I choose and the hyperparameters that you choose. So you do better by 3%. Yeah, that could be just because you pick better hyperparameters. And yeah, so that's interesting because in the field, yeah, a difference of 3%, it can be quite large. So that's often you see some results that do 1% better on a certain data set, and then they make all sorts of claims about superior performance. So don't never use that term. It sounds very cocky and arrogant.
The black magic is experience.
Black magic is well, that is your skill in black magic.
Yeah, right.
The black magic is the tuning, and yeah.
Jan, we have a question from Nikhil Reddy. Nikhil, can you unmute yourself and go ahead? Nikhil.
Hello.
Yeah, please go ahead.
Yeah, I have this query that recent developments in neural architecture search or AutoML architectures.
Yeah.
So, what are your thoughts on that? Like on recent?
It's very good. So it's very good that they're moving in that direction. But in practice, well, often this is very expensive. There is, of course, work that tries to do it cheaply, but often this hyperparameter, this neural architecture search is quite expensive. So you need several GPUs. And often they have their own hyperparameters. So you're kind of moving the problem. So this meta learning, this neural architecture search or AutoML, they often have also their own choice of hyperparameters. And then, so I think this is the way to go. But in practice nowadays, so in my lab, so my PhD students, they do it by hand.
Good. Nikhil, does that answer your question? Okay. Thank you, Jan. Please go ahead.
Yeah. And then there's the plot here on the right. And there you see the accuracy on the y-axis. And we have 3 lines, novice, medium, and expert. And the number of, so we kept track because we have this web interface, we track everything. So we could store everything they did. This is the first try, second try, third try. So how many tries of hyperparameters there were. And then you can see that experts already start higher than especially the novices and medium. And you see they find a good result much quicker. So because probably they are more experienced. So what we also, so I don't think I discussed it in the presentation, but what they typically do, they leave most values to default. And then after they found a good default, so they only start to tune the most important parameters. So they know which ones are the most important, and the rest they leave to default, and only then they start to fine tune. But the experts, they read a higher accuracy faster. So they get a higher accuracy overall, but they also can do it quicker. Now, some conclusions. So many papers kind of assume already that human skill impacts accuracy. But we are actually the first that actually shows this with some results. So people always, so one of the reviewers said, yeah, it's well known. Of course, reject. This is well known. Yeah, okay, if it's so well known, yeah, please give me a paper then. There is no paper because it's all assumed. And this is, yeah, so now there is one.
No. But it has been written very well. The narrative, it's very good. Even though the idea is this thing, it has been well researched and well, the inference is very good.
Yeah, yes. And so we find that indeed it's a bit of, yeah, very unsurprising that more experience correlates with more skill, as you would expect. And then we have some recommendations. So if you want to, if you're publishing your work, please always share these hyperparameters. So they can be very important for people who want to reproduce your work, or share your code with the hyperparameters, because it also may matter which framework you use. So TensorFlow, for example, PyTorch, it may not always distribute one-to-one. Yeah, if you write a paper or you do your thesis and you're comparing to a certain baseline, yeah, it's good to be fair to them. So it's, if possible, if you have their code and you run it on a new data set, yeah, you may need to tune their hyperparameters again. And if you want, try to do this fair and also write about this, that you optimize your baselines as well. Yeah, and I really, so if I'm a reviewer, I'm reviewing for CVPR, ECCV, ICCV, yeah, most of the computer vision conferences. Yeah, if I see the claim superior performance, it always makes me itch. I don't like this term. So it places too much value on accuracy. And this is, yeah, as scientists, we should actually care about understanding. So if you have good results, we will see it in the bold numbers. There's no need to rub our face into it. So it will also be good to make these bold numbers less important, because as we show here, even for experts, there may be variance. There may be already 5% variance just because hyperparameters are different. So we should care more about the novel ideas and the novel insights and less about bold numbers. But okay, this is something, I'm not the first to say this. So as a field, we are struggling with this. So this is, in a nutshell, is the paper. So I'm not sure if you have any more questions.
Yeah. Please share the parameters set by the experts. That will be very good to see. Yeah.
So I will ask Kanaver. So we had a small prize for the winner. And we gave all the participants, we gave them cookies and drinks and all that. But we also told them that they could win something, and there was a winner. I don't know what we gave them anymore. I think we gave them a pitchfork. Tuner, the best tuner. So you could tune. Ding.
Okay, understood. The prongs one with 2 prongs.
Yeah,
got it.
Yeah, this you hit it.
So there's a question from Praveen that he wants to know your thoughts on using deep reinforcement learning for hyperparameter tuning.
Yes, so this is a good idea. So you can neural architecture search, either using reinforcement learning or using RNN kind of structures or using other kind of techniques. AutoML and neural architecture search, this is what we should be using. But in practice, often it's not.
And what was the machine that the participants were allowed on? Was it a common machine, right? I'm assuming it was a common machine.
Yeah, so we had actually 4 machines for clients, and then we had them connect to a server, and then the server had a 1080 Ti GPU.
Good.
And then the time limit was 2 hours.
Oh, and how much time did it take from the idea stage to finally submitting the work?
That's a good question. So I think most novices took longer, and experts were also done quicker. But I don't think most people left before the 2 hours. But some people really took it very serious, so they kept on tuning until the very end.
So there's another question from Nikhil. What is the major concern for reviewers on this paper?
Yes, that's a good question. So, yeah, they claim this is well known, not novel, no novelty, well known, reject. That's one reviewer. We also had people say, okay, British machine vision. Yeah, this is not machine vision. This is, I don't know. Oh, sure, you do an image task, but yeah, I don't know. It belongs in this conference. They have a bit of a point, but yeah. So where else would be everyone? Yeah. So where else would it fit? And we can also turn this around and say that in a way it fits everywhere. Interesting for everyone.
Another question is, how do we know that our hyperparameters are optimized or nearly optimized?
Yeah, you never know. Maybe an expert who is slightly better than you, they may do better. That's one of the problems, but it does, yeah. So the 5%, so yeah, to me it's reasonable. So if you look at the expert performance in this graph here, so in this box plot, so there's 5% difference. for me, that means it's close enough. It's more about people who say that they reach superior performance by getting 1% extra. Yeah,
Right.
is that true? I don't know. So in practice, in production, companies, they don't really care so much about the hyperparameters. They don't like to do this. They don't want to find the very exact local optimum where your parameter is best. They try, if you can minimize this, it's an advantage. So you
Right.
want a robust model. You don't want a model that's very sensitive to small changes.
Right. One more question from Akash. He's asking that, do you think the system that's training the model makes a difference, since different systems handle floating point values differently? I've seen such things make a difference in deep reinforcement learning system, but what's your thoughts on such issues in computer vision?
Yeah, so they use the exact same machine. So it's all sent to the exact same GPU.
Right. Right.
So, Jan, I know you review tons of papers. So, what is the common mistake that all of them make, or what are you looking for that immediately catch your attention?
Me, I want to learn something.
Mm.
So if you show me something interesting that I didn't know before, then I will be on your side. If you write a paper where you describe your new architecture, yeah, and you get good results, and you just describe the architecture without any motivation or without any intuition, and you don't test this intuition, so you don't show that this intuition could be true, then I'm not going to be too much on your side. But okay, I will be on your side if the results are amazing.
So,
The results have to be very good, more than 1%.
So we need to first justify why there was a need to introduce a new architecture in the first place.
That's very important. Motivation and why do you do something? Why do you make this choice? Why do you make that choice? That for me is, if I don't see this, then I'm lost. Then I see, okay, and then you take this, then you do this. You run this attention module on this this sort of layer, and then okay, yeah, good for you, but why? Okay, nice. Okay, and then you tune it, and then you get good results. You get 1% better. Yeah, okay, yeah, good. I like to learn something new, something that I didn't know before, or something that you investigate that I didn't think about before. Something that, and it doesn't have to be a new architecture. So everybody now has new architectures. So we were drowning in new architectures.
Yeah, Nikhil has one more question. Nikhil, please go ahead.
Yeah, I have this question that for incorporating the prayers into the deep neural architectures, like, can you suggest some resources or?
Yes. So that's my current research topic, and we organized a workshop at ECCV about visual inductive priors to add prior knowledge to deep networks. And well, the best example is the convolution operator. So if you add convolution to deep learning, you get a CNN. And CNNs are always now, if you do images, everybody uses CNN. And the CNN, so CNN, you slide your window and you're sharing features over all locations. So that means that it doesn't really matter if the object appears here or if the object appears there. That's the inductive prior that the convolution operator has. Actually, at CVPR, I had a paper that shows that current CNNs, they can exploit position information because of boundary effects, but that's maybe a side note. But what kind of priors? Yeah, this is what I find very interesting. So at ECCV, I have a paper that tries to include priors about straight lines by using the Huff transform. Well, these group equivariant convolutional networks are quite interesting because they also incorporate prior knowledge about the transformations that are there, and they are very data efficient. So they indeed allow, you need much less data to get reasonable performance. Yeah, so this is a good question. So these are kind of the topics that we're working on.
Good. Nikhil, maybe you can just introduce yourself. What are you currently doing so that Prof knows what is your current situation? Yeah.
Yeah, I'm a PhD student at IIT Delhi.
Good.
Yeah, I hope you know me. I attended previous talks as well.
Yeah. But Prof is talking to you for the first time.
Yeah.
Good.
So
Uh,
I'm currently looking at incorporating geometric trees into the computer vision task.
Interesting.
Yeah, I have attended the present your workshop as well.
Very
Nice.
good.
Like I have watched your workshop.
Super.
Yeah.
Super. Very good.
We had some nice keynotes, I think. Yeah. So the
Good.
keynotes were interesting. I think they should be available online, I guess.
Yeah, one more question from my end. I was going through your previous research work and I found some work on optical flows. And some of my friends here are working on optical flow for motion perception to incorporate it in an autonomous robot delivery system. So I would like to know that is optical flow from what we have heard, it is highly competitive. We should search for alternatives before diving into optical flows. And would you agree with the common notion?
Yeah. So in action recognition, for example, well, there was the two-stream network. So they take two streams. One stream is RGB and the other stream is optical flow, and they work quite well. And then even with 3D convolutions, where you have space-time convolutions, optical flow still seems to add something. But we're now in action recognition trying to get rid of it because it's quite expensive to compute. So there are methods that use optical flow, for example, during training, but not during testing, or they try to incorporate optical flow in the architecture itself.
Any alternative you would suggest to manage the cost efficiency?
Yeah, so some time ago we looked into phase. So there is also this, yeah, there's this paper. It's a great paper by MIT. It's on Eulerian video magnification, and it uses. So I'm not sure how. So in the Fourier domain, you have the phase and the magnitude, and you can compute the phase of a signal over time, and that's different from optical flow. So optical flow tries to
Pixel movement. Yes.
Yeah, well, yeah. So pixels themselves, they always stay the same, but the object, it moves from here to there, and then you have a vector from here to there.
Right.
And the Eulerian perspective is that you don't have a vector, but you stay in one grid cell, and you measure the change.
Right.
So this is a different. So this MIT paper, Eulerian video magnification, it's a great paper that explains these differences. And we looked at this also for video, but so far we couldn't get it to do so well. So there's an opportunity there if you're it could be hyperparameters.
And if from your perspective we ask what is one of the most unexplored and unexploited domain in computer vision, is there any? And if yes, which one?
They're trying to do literature review through you.
Yeah.
No, because most of us, we are working in scene understanding, video understanding, and some of us are thinking to switch to medical imaging because there's still much to explore over there. So I'm just asking the common doubts of our research group.
Yeah. So okay, maybe I'm getting old, but there is of course lots of prior work on images, and I feel sometimes that the deep learning is reinventing the wheel a bit. So there is, so for example, there's this blur pool paper that so it tells you that if you do pooling, you should first smooth a bit, because if you don't do that, you get aliasing effects. So if you smooth, you get aliasing, and that's something that we've known in the image processing community for a long time. The same with our own paper at CVPR that shows that the convolutional network, it can encode absolute position by exploiting boundary effects. So boundary effects are also well known. There is something called scale space theory that talks about how objects, if objects are close by or far away, how the scale could be analyzed. So I think there is still unexplored and kind of low-hanging fruit, kind of, in looking at old-fashioned stuff and put it. So what we did for the Hopf transform, so I'm not sure if you know the Hopf transform, but the Hopf transform, it tries to fit straight lines. And typically the original Hopf transform, it uses the Kenny edge detector. So the Kenny edge detector, it looks at the gradient of the image, and it looks at the second derivative and it thresholds. We want to keep the knowledge about straight lines, but get rid of the handcrafted feature extractor. So you want to get rid of the Kenny edge detector. We want the features to learn by the network, but the knowledge to keep there. And there is lots of knowledge in the old image processing, signal processing, computer vision literature. And I think that's a bit unexplored. So the deep learning community is a bit reinventing, known wheels a bit.
So there's one question from Akash. He says that currently we've seen a lot of papers trying to use self-attention or transformer architecture for doing computer vision. Do you think we can get over the current issue with CNNs like rotational and affine invariance using self-attention architectures and learn positional encodings? Or maybe in future, can we see better architectures that make CNNs more generalized?
Yeah, it's a good question. Yeah, so of course, self-attention in its vanilla form, it doesn't use any position information. So that's, in principle, it should be the location of the pixels don't matter. But okay, if you're starting to extract patches, then again, the patch itself has a certain orientation that will then, of course, play a role again. And if you do these positional embeddings, then you put position back. So there was a paper, was it at ICML last year, that they showed the self-attention on images. It can learn the convolution, but it's it can learn more things. So I think you could see it as a graph network. You can also reinterpret it as a Hopfield network. There was a recent, so Hopfield networks is all you need, I think, is the title of the paper. That's a great paper that links self-attention to Hopfield networks. So that's very good, because then then it really is about understanding. So that really, for me, a light bulb went up in my head seeing that paper. So that was great. So there was this 16 by 16 words, I think, is all you need. No, 16 pixels. I forgot the title.
Which was that paper, Jan, in ICML?
Okay.
Yeah, maybe I'll email you. Or
I have to. They show that if you do self-attention on images, it can learn the convolution operator. Because it's more flexible than convolution. Okay. So it also that means, so in this 16 by 16 patch paper, so they say that self-attention does better than convolution if you first train it with 300 million images.
Whoa, 300 million.
If you do that, of course, it's going to do better because it's more powerful.
Yes.
If you're more, it's a bias variance trade-off. If you have more power, you need more data. So to me, the conclusion of that paper, I would actually flip it around. So that to me, I would say, well, convolution, okay, maybe it does 1% worse, but it doesn't need these 300 million images to pre-train on. So
that
to me,
paper,
convolution.
That paper was trending a lot on Twitter these days.
Yeah, exactly. It was a bit. People said bye convolutions. And
yeah, right.
A bit of hype. But okay, there's this group equivariance. I'm not sure if you're familiar with this. So it may have started with the scattering transform or even before that. So there's also the work of Max Welling and Taco Cohen. So they can incorporate rotations in your network. So they say translation is on the translation group, but you can also have a rotation group. You can even have a scaling group, even though that's a semi-group. But so there is work there that tries to add prior knowledge. There is now even, I think there's now by David Romero. He's a PhD student at the Free University in Amsterdam. He did this for attention, to come back to the self-attention. So you can also do this on the positional embeddings to make them rotational equivariant. So that's very exciting work, I think.
Okay. So I think, see, what I feel is for students, even though they have a good idea, they don't do one proper literature review. Second, they really don't write it well enough, highlighting the main contribution. So that is really hampering their thing, because I also see a lot of manuscripts. What I finally see is that like the writing itself, it's not clear enough, or the reader gets lost in all the, either they make the introduction massive, contribution very less, or they don't interpret the results properly. So I think that is where, in this, if you see, it's very crisp. You get to the point really quick. You elaborate on what are the things that were done in the study, and finally, what is the inference. So writing is really a skill that has to be developed. That is what it is lacking.
Yeah, so it's very difficult because it's the same as writing code.
Yeah.
If you're writing code or writing text, at some point you just see what you mean. You no longer read what's there. Oh yeah, I mean this, and there I mean that. And it's the same with coding. Oh, here I do this, and here I do it, and there I do this. And you don't actually read it anymore.
And also, I find it when somebody, because I also guide a couple of students, when somebody gets excited about one idea, they are not willing to let it go, because that idea might not result in anything. But they try to fit the entire narrative to that idea instead of letting go of that idea. That is also a big problem.
Yeah, the first thing that you should try to do is break the idea. That's the first thing you should try to do, because
poke holes in the idea.
You can always try bigger architectures and bigger data sets. That's something you can always do. But you don't want to find out 6 months after training your ImageNet huge ResNet 1001 model that the idea wasn't good. And I have many bad ideas. Some of them turn out to be okay, but never in the first try. Always they need some. So this is the idea, and then you go into a slightly different direction. Often the main idea was in a good direction, but not spot on.
Yeah. And how do you deal with papers when you get papers for review which are not in your domain? So how do you?
If they're really not, then I don't. I can't do that. Or I just set my my certainty to low. So now I get many reviewers that set their certainty to high, even though I see, okay, the review wasn't very great, but you're very sure of yourself. It's not about ego. It's about honesty, and it's about, I don't know. What I find, so in my classes, if I let students review papers, they're so harsh.
Yeah,
are the harshest, and then PhD, the first year PhD students, they're also they're so harsh. But the higher it seems, the more experience you have, the harsher the reviews are.
Yeah, because the lesser patience you have as you move up, because
I don't know. So I'm more forgiving. If there's a good idea, you can have some small mistakes.
See, I have been a reviewer in certain journals where it has been rejected after the second review, because first they felt okay, it is okay-ish, and they asked for some clarification. But the answers to the clarification was totally, they just reiterated sections of the paper. So it angered the reviewers. So I don't know, it's a slippery slope. But good.
Yeah, the reviewers are human, eh? You should keep That's a problem.
Yeah. So good that you were able to convince Kanau to take this topic. Very good.
To take this topic. Yeah. He also, in the beginning, he also liked it. But he really got into it at some point. So that's also with good students. Yeah, at some point in the beginning, you give them a certain topic, or you constrain it, and then in the beginning maybe you lead them a bit more. And at some point they start to lead you.
Yeah.
That's where you want to be, because I can't be the expert on all. So Kanav really did a great job. Good. So he became the expert at some point, and then took us by the hand.
They are into it. What is he doing now?
I don't know what he's doing now.
Good. Maybe you'll find out. We'll email him and find out. Any more questions, Shambhavi?
I guess not, sir. And it was really kind of sir to oblige and give a talk and deal with all my small little doubts.
My pleasure.
Thank you, Jan. Thank you very much. Thank you for your time. We greatly appreciate it because nowadays everybody is so busy reviewing because now we have more papers than usual to review.
Exactly.
Like for CVPR submissions, I couldn't get speakers for 2 weeks of November. Everyone is like, let's do after 14th of November.
Yeah, it's true. But you asked earlier, so I didn't.
Yeah.
I didn't realize
Good. Very good, Dr. Jan. And audience members, thank you for your questions. If you have any more questions, please email Dr. Jan. He will definitely get back to you.
Yeah.
And thank you for your time, Dr. Jan. It was really good. Great work from your research group.
My pleasure. And then thanks for inviting me.
Yeah. Thank you very much. Have a nice day.
Have a nice day.